part, we will talk about the technical challenges and the technical aspect of those, but we will not implement that in the mini-based system. Let me be clear. Okay, we will cover those aspects, but we will just not doing that from the programming aspect. Okay. So there is a significant component of programming assignments in this class, and so that leads me to before I do the grading part, let me just finish the introduction to the overview of the class. So after we finish the kernel of the relational database systems, we will branch out to some of these newer systems, like NoSQL system. You might heard of this. So it's going live.
Yeah, it's online.
All right. Okay. Thank you. Let's give a round of applause to Okay. So once we finish the relational kernel, we will go to this space called NoSQL systems. NoSQL is a relatively new concept that has been developed in the past 4 or 5 years. Remember, NoSQL doesn't mean no SQL. It means not only SQL. So the name actually is for it to complement a relational database system. Okay, and we'll cover some aspect of that. In particular, we will talk about things like MongoDB, HBase very briefly. Then we will move on to some of the analytical engines. So slowly diverging from the data management aspect a little bit, but moving to the analytical engine aspect a little bit, such as MapReduce and Spark. So we'll try to cover those as well. So it will be a fully packed class schedule. So we really need to make good progress. I cannot promise that I will be able to cover everything set due to the schedule constraint, but we will try to move ahead as quickly as we can, so that you guys are exposed to all this different kind of data management system out there. Okay. All right. So that being said, there is a syllabus PDF version available online. I don't think I need to go over that because pretty much that's what I said just now. But if you are really interested in knowing all these details, like the overview and the main stuff of the class, go check out this PDF now. Okay. It's online. Textbook. So we have a textbook which is the database management system by Johannes Gerker and Rakeshman. Both of them are now in Microsoft. The first author was a full professor at Wisconsin, and then he moved to Microsoft. The second author was his PhD student. After he graduated from Wisconsin, he went to Cornell, became a full professor over there, but now he left Cornell and joined Microsoft as well. Okay. This textbook, I recommend that you get a copy of this somehow. But it's not. I think the price tag is hefty. It's like $100 or something. So either you get a used one, or or you just follow the lecture slides. And I think it will be fine just following the lecture slides. So if you are not sure about whether you want to spend that much money on this book, just wait for 1 or 2 weeks, see how it goes, then make the decision. So don't rush and spend $100 on this yet. If you are not sure whether you want to buy a textbook or not. We do also have a recommended reading, which is a book from Stanford called The Database System, The Complete Book. There is a link for that book as well. This one definitely, I don't think you need to buy it, but if you somehow can get a hand of this book, it will be a useful complementary reading to the first book we mentioned. And both books, I believe, are available in library that you can borrow out. Okay, schedule-wise, I think you all know where to meet and time. Office hour, my office hour will be Tuesday and Thursday from 9:30 to 10:30 in my office. And we have 2 TAs. One is Ray and one is Roshni. They have their office hours listed over there. We have pretty much every day covered, Monday to Friday. Okay, between 3 of us. Feel free to talk to either of us in any given day. Their offices for the TA office hours are not fixed yet, which will be finalized within this week. Once I hear some update from the front office, they will let me know and I will update the website. Okay. And we also have this is where I will post lecture slides written assignments, and project. So we will post written assignment solutions here as well. There will be a password to be distributed out to you. And once you have the password, you can log in and get access to written homework assignments and solutions and some of the sample questions we have. And if you feel that those written assignments do not provide enough exercise for you, which I think they will, but just in case, there are more exercise you can do on your own. In particular for this textbook I mentioned earlier, which is this one. For this textbook, for each chapter, after the chapter, they have a set of questions, right? And I obtained the solutions to all the odd number questions for all chapters, for all odd number questions, right? So if you want to do some exercise on your own, go after those odd number questions behind each chapter of the textbook. That way you can check against yourself to this solution manual, which is posted, excuse me, which is posted right here. Which is posted right here. Okay. All right. Let me. We do have two interpreters in the class. They will do American Sign Language translation for a student. So just to make a note on that. In addition to this homepage, we also have a Canvas homepage that's set up, and you should be able to access this using your UID account. What it is for is I really like the discussion forum functionality of this, which enable an interactive place for us to discuss, post a question and all that. So you can utilize this discussion function here. I will also use this to make announcement and posting your grades and things like that. Okay. That being said, there is also, I forgot to mention, there is also a mailing list that's been set up. So I want all of you to sign up for the mailing list. You may wonder, so we already have Canvas. Why can't you just send email over there? It's just that having a mailing list is much easier for me to send out mass emails instead of go through this Canvas. Canvas can be slow at some point. So I will use the mailing list to make announcement and things like that. And feel free to post your question to the mailing list as well. So in addition to the discussion functionality here, you can also utilize that mailing list to post your question and initiate a discussion. Okay? Any questions so far? No? Okay. Let's talk about how we do the grading for this class. So we're gonna have a 40% programming assignment, meaning that programming assignment counts for 40% of your grade. So which is a significant component of your grade. All right. And there is a midterm test and a final test. We will also have written assignments, but those ones I will not ask TA to grade your written assignment. The reason being that from my past teaching, I found that most of you do pretty well on written assignments because you discuss and all that, and you have all the time you need to get the solutions down. So I will not grade the written assignments. Rather, when a written assignment is due, I will release the solution, and you can check against yourself. And for those parts, you are not sure whether your solution is right or not. If your solution is the same as my solution, fine. If it's not, and you are not sure whether it's right or not, then you can come in and check with me or the TAs. So we kind of ask you to do self-grading for written assignments. Okay? And we will also have 5 or 4 in-class quiz. These are random quiz that I choose at different lectures I give out. And these ones, nobody will grade those quizzes. But once a quiz is done, I will show solution. I will go over the solution right after a quiz in class. So that gives you a way to test yourself as well. And without pressure, because those are not graded or counted towards your final grade. But it does provide a way to check your progress and make sure you are on track. Okay? Any question on that? programming assignment is done by yourself. There's no team to be formed, so you are on your own. But you are allowed to discuss among yourselves. But just remember, don't copy code from each other or from online resources. I'm very strict on this. If you copy once, you will get 0 for that product. If you copy twice, you fail the class. Okay? And we have software in place to detect plagiarism in bytecode level. Right? We don't just check your source code. We check the bytecode that your source code compile into. So by simply changing random the variable names, flipping source code segments, all those tricks will fail. We will be able to detect all of this. Okay, and let me make it very clear. I'm very serious on this, so don't even try. Okay, don't even try. Okay. All right. Any questions? Wait. Let's get started. At the bottom of the page, we have the email address of the TAs and myself. Oh, one more thing I'd like to mention for the student that needs the translation. I think we also need a note taker. You will be paid. The rate is to be negotiated offline, but if you're interested, let me know. Drop me an email. We will go from there. Okay. So let's get started. So the first thing, as I said, in order to understand a database system, we need to understand what is a database and what are the applications that drive the need for database, right? So for that, we will start with this most popular data management model out there, which is the relational model. So oftentimes you see this word, DBMS, this abbreviation, which stands for Database Management System. And there's one word that's often omitted from this, which is RDBMS, which stands for Relational Database Management System. Because Relational Database Management System become so popular over the last 20, 30 years, this R is often omitted for convenience. Because by default, when you say DBMS, it's always RDBMS, Relational Database Management System. But of course, the picture is changing. We have a newer system coming out in this space, such as, like I mentioned just now, NoSQL system, which complement this, right? But in order to understand all of this, guys, we start with this R, relational, this word, relational. So there is a Turing Award winner who did contribution to the foundation of the relational model. His name is Cobb. Right? He won the Turing Award I think in late 70s or early 80s for his contribution to the foundation of the relational model. Of course, you guys, if you follow the news, you know this year's Turing Award also goes to a database guy, Stonebreaker. For his contribution in building open source database management system. One of the cornerstone of his work is PostgreSQL. Right? PostgreSQL. Okay, so, but all of these systems that I have mentioned, PostgreSQL, Oracle, the System R by IBM, DB2, SQL Server, MySQL, they all based on the relational model. Cobb has built the foundation for it. When he was a research scientist at IBM Research. So the relational model, the first thing relational model is what we call the data model. So data model is a way to map the user view of real-world objects into something that a database can understand. I'll give you an example. You guys are students. In a database management system, how would I model you guys, the information about you guys? Well, I will design something like this. This is what we call data model. And in particular, this data model comply with the requirement of the relational model. In that sense, in the sense that it starts with a relational name, student is a relational name, and you are free to choose whatever name you want to describe your model, your data model. So in this case, I choose student because I want to describe you guys. Okay, so you often choose something that's meaningful, right? And then the remaining part is what we call the schema of the data model. And the schema basically is a list of pairs, and each pair has an attribute name and attribute type. So it's a pair of attribute name and attribute type that describes structured information about your real-world object. So there is a keyword here, which is structured information about your real-world object, right? So why I call this structured? Because even without seeing any actual data that go into this model, by just looking at the schema information, I know exactly how each record should be organized, which is structured, right? If you compare this against a text file or log data, you immediately see the difference, right? If I give you a text file or a log file, you will not be able to infer a unified structure to describe all the entries in it, right? Some of them may be different from some other entries over there, but in a relational data model, once you describe the schema, every data entry go into this particular data model should have must follow the same structure as stipulated by the schema of your data model. Okay. So why study relational model? I think I can skip this slide. I give you a long list of database systems that use this model, right? So there is a strong motivation for us to understand this. So once you understand the concept of data model, now we go on to the concept of a relational database. A relational database is a collection of relations, and each relation has two components in it. One is the schema information, which we have just seen, right? That's student, that's a schema. And the other component for relation is the instance of the relation. So what is the instance of a relation? Well, the actual data in it. Okay? So let me see whether I have an example. See, so here is the example. This is a relation. The top row, the first row is your schema information. Of course, I omitted the type from that schema, but it has the name and the list of attributes as we described. And the three entries down below form your instance for this relation. Of course, once you have a schema, you may have many different instances all comply to that schema. Okay? You may have many different instances comply to that schema. How many possible instances are there? Well, that depends on the domain size of each attribute. The total number of possible instances that can go into a relation is simply the multiplication of the domain size of all the attributes for that schema. Okay? There are some keywords you might want to pay attention to, such as cardinality, which describes the number of rows in an instance. Okay, so that's a keyword we use to describe that. And we also have a keyword called degree of arity, which describes the number of columns in a schema. Okay, those are just some keywords that you want to remember so that you are clear in our discussion. Okay, so in this case, cardinality is 3, arity is 5. One question we ask is, do all values in each column of a relation instance have to be distinct? Okay, which translates, so let me rephrase this question. What that says is, if you look at a single column, any column, right, from your relational, from a relational table, whether all the values in that column must be distinct, all the values in that column must be distinct. Well, the answer to that depends, right? The answer to that depends. If you ask me the name column, answer is no. Obviously, we can have students who share the same name. But if you ask me the student ID column, the answer will be yes, because each student must have a unique student ID, just like each of you has a unique, distinct UID, right? So why is that? Well, this has to do with a concept called key, which we will discuss in a little bit. But the bottom line is, to remember this. For any single column, the values for that column, they do not have to be distinct unless it's a key column. However, if you look at each row as a whole, each row as a single record as a whole, then no two rows can have same values on all attributes. Okay, no two rows can have all same values on all columns, which means no two records can be identical in a given instance. No two records can be identical in a given instance. They must differ by at least one attribute value. That makes sense because the goal of database is to store data, right, from the name. Right? Data is for data, just like airbase is for airplanes. Okay. So why you want to store redundant data? There's no point for you to do that, right? So that's why in one instance, no two records, no two rows can be identical, right? They must differ by at least one value. Okay, so that's pretty much the basics of relational model. Fairly simple, right? Very simple. A bunch of relations. Each relation has a schema and an instance that organize into a table format. Okay. Then on top, okay. So that's where your data goes. And of course, once you know how you store your data, you want to be able to manipulate your data. In other words, retrieve your data and update your data and so on and so forth. And in order to do that, we need to have a language, right? Just like when you interact with a computer, you write a program in Python, in C, in C++, in Java, in Ruby, you name it, right? When you interact with the database system, you use a particular language that over the years becomes the most popular and the standard for interacting with the database system. It's so standard, and it's so powerful even for no SQL system. They slowly have to build a layer on top that support SQL and then translate into whatever they are doing natively. Like for example, if you look at Hadoop, right, which is really popular, a popular MapReduce engine, you have Hive on top. Right? Hive is another open source project that built on top of Hadoop, which basically provides a data warehouse-like interface for users to utilize data stored in a Hadoop DFS system. And Hive basically has an SQL layer. Initially, we only have this, but then the demand is so strong that they have to go out and build this in order to promote the usage of Hadoop, so that they have a SQL layer on top. Even though this is a NoSQL system. It's kind of funny, right? When they call themselves NoSQL, but they have to build SQL. But then they come out and say, okay, NoSQL doesn't mean NoSQL means not only SQL. So we do support SQL and other things. Okay. Okay. So excuse me. So SQL stands for structured query language. S is for structured. Okay. Why is it called structured query language? Because it was initially designed for interacting with relational database system, and relational model, as we have just argued, is structured. So the language interacting with it is a structured query language. Okay. So it has, if loosely speaking, we can classify SQL into two categories. The syntax of SQL into two categories. One is DDL, one is DML. Data definition language and data manipulation language. For DDL is for creating a table, modifying your existing data, insertion, deletion, and all that. DML is really for retrieving data, okay, based on different query syntax. For example, these are a bunch of, the first few are DDL syntax. The last one is the DML syntax. Don't worry about the details. I will devote one or two, I think maybe 2 lectures on the details of SQL. And we will go over this in subsequent lectures. Here is just to give you a preview of what it looks like. So, for example, how we create a relation in SQL. So, you just to create a table, the keywords that are capitalized are syntax reserved for SQL. The small case letter words are those ones that you supply as parameters in constructing your query, in constructing your statement. In an actual system, though, they do not make such distinction. You can use small case or capital letter for either of them. They do not really care. The system doesn't really care about that. So to create a table, all you need to do is to specify the schema for that table. You don't have to specify the instance for that table. All you need to do is to specify the schema of that table. Okay? Like looking at these two examples. Okay? If you want to update or to create an instance for a schema you have already produced in your database, what you will do is use this syntax, like insert into and delete from. These are fairly simple, as you can see. The first one basically is to try to insert a single row into the student schema. Okay, and the only requirement there is to make sure that you have the right data type for the right column. You cannot, for example, insert a string to an integer column. Right? That's the only thing that you want to pay attention to. Okay, and delete followed by a where statement, which is to followed by a Boolean expression. So it will remove all the records from this table, from the instance of this table, when this condition is true. You evaluate this against every single record in that table. Whenever a row makes this statement become true, then that row will be qualified for the deletion. Okay? That's the way you interpret this. You can kind of think of this as a for loop, going through each record in the instance. Whenever the condition is true, then you do the thing specified here. Okay, which is delete in this case. Okay, I mentioned the concept key, so now let's do a closer look at this concept. This is one of the fundamental concepts in relational model, so it's really important that you understand this. So there are several different concepts associated with this key definition, right? First of all, we have this concept called superkey, which is nothing else but a set of fields if no two distinct tuples or records can have same values in all key fields, right? So what that means is you view this as a set. You view this as a set. It's a set of fields, right? And no two records can have same values on all attributes in a superkey. As long as they differ by one, then it's okay. But they cannot be having identical values on all key fields. Then, if that's the case, this set of fields is what we call a superkey. Give you an example. Remember, first of all, it has to be a set, right? So when you see SID, this is not right because this is not a set. So you have to make it a set. Make it a set. Okay, now this is a set. Of course, it's a set with a single attribute. However, if you look at this, obviously no two records can have same value on all key fields. In this case, only one field, right? But no two records can have same SID value. So obviously, this statement is true. That's why this is a superkey. This is a superkey. Okay, let's go on to another example. What about name? Student name. Well, obviously no, because your two records can obviously have same values on this. Okay. What about SID and name? The answer is yes. Okay. Right? Why? Why this is a super key? Because first of all, it is a set of fields. In particular, the set with two fields, two attributes, and no two records from the student table can have same values on both fields. You may have same name, but you can never have same SID value. So as a whole, if you view this as a set element, no two elements in this set can have same values. Right? You can have, for example, you may also have, right? But you can never have another, this is impossible. Okay? You follow me? So that's the concept of superkey. There is So that said, there's always, combining with the fact that we introduced earlier that no two records can be identical in a relational instance, we immediately have a default superkey for any schema, which is the schema itself. Right? Combining these two facts, you get that conclusion. Right? Okay, now let's move on to the concept of key. We understand superkey. Now let's move on to key. What is the key? A key, first of all, it is still a set of fields. Okay, that's still the same as the superkey does, and it must be a superkey to begin with. And in addition, no proper subset of the fields is a superkey. No proper subset of the field of the fields is a superkey. What that means is, if we look at this, again we go back down, right? If we look at this, what is the proper subset of this set? There's only one proper subset of this, which is an empty set. That obviously cannot be a superkey, so this is a key as well. Not only it's a superkey, but it's a key, because no proper subset can be a superkey. It has only one proper subset, which is not a superkey, so by definition it's a key. And class itself is a superkey. Second, what about this? Well, this cannot be a key because it's not even a superkey. What about this? Yes, it is a superkey, but what are the proper subsets of this? Well, you have this, you have name, and you have empty set. Remember, we're talking about proper subsets, so the set itself is not a proper subset. You follow me? So among these ones, which one is a superkey, which one is not? This is not a superkey, etc. This is not, but this is a superkey. Then by definition, this cannot be a key. Because there is a proper subset of this guy, of this set, that is a superkey. So superkey capture from this example, you see the intuition behind the definition of a key. The intuition is I want to capture this minimal sense, right? This minimality in some sense. A set of fields is a key if it is minimal in size. In the sense that you cannot remove any attribute from this set and still be a key. Still be able to uniquely identify a record from an instance. In other words, every single attribute in this set is needed in order to uniquely identify a record. When that's the case, you have a key. And you may have more than one keys for a given relation. For example, going back to the student example, what are the keys I have? Student ID is the key, as we have argued. Login is another example. Login is another example. Right? Login is another example. And of course, I may also give you some additional constraints in my user specification that will provide additional keys. For example, I may argue, okay, no students who have the same name should be given the same GPA values. If I tell you that, of course, by default, this is not the case. In any university, student with the same name can have same GPA values. But just for the argument's sake, let me give you that argument. Okay, let me give you that constraint saying that, okay, no students who have same names can have same GPA values. Okay, when I say that, what do you get? You get another key, which is the combination of name and GPA. This, by definition, is a superkey because I just mentioned no two students can have same name. No two students with the same name can have same GPA values, which means the combination of this must be unique across all records. So this is a superkey. But whether this is a key, well, it is a key. Why? Because some of you are, if I don't give you that constraint I just mentioned, then this is not a key. This is just a superkey. Okay? But now given the constraint I gave you, if you think about it, the fact that name, what are the proper subset of this? You have three proper subsets of this, right? None of this is a superkey, but itself is a superkey. So this is the key. The constraint I gave you make this a superkey. Without the constraint I give you, this itself is not a superkey, so it cannot be a key. But with the constraint I give you, this becomes a superkey. and none of a subset is a super key. So this becomes a key as well. Okay, so this gives you another aspect of key, which is what we said just now. Keys is, in some sense, key are those set of attributes that are minimal in size. But that's with respect to the set of fields themselves. You cannot compare against two keys and argue, okay, one has a smaller size, and because of that, the other one cannot be a key. That's not true. It's minimal in size with respect to itself. Do you follow me? So the fact that this is the key, and the fact that SID and logging are keys, do not exclude the possibility that you may have another key of size 2 or even size 3. Do you follow me? So it's minimal in size with respect to itself, not to compare against multiple keys. Yeah.
Can you please repeat the last example of SID and logging?
Oh, these are keys, right? Very easy to say. These are keys. Why? Because, by the way, feel free to ask questions anytime, right? You can interrupt me anytime during the lecture. So, why these are keys? Because this is a super key, because no two records can have same SID value. No two records can have same logging value. So these are super keys. And the only proper subset of these guys are empty set. And empty set cannot be a super key, so by definition, these are keys. Okay. Alright, so those are concepts related to key. And there's one more concept I have to introduce with key, which is two more concepts, sorry. Because we have more than one keys for a given schema, we potentially, right? I'm not saying we always have more than one key for a schema. Potentially we have more than one key for a schema. So what you will do is choose one of them. You as a database designer, you choose one of them as the primary key for your schema. You can choose any one of them, any keys as your primary key. And the remaining keys automatically become what we call the candidate keys. It's kind of like a presidential candidates, right? You have to be good enough to be a presidential candidate. I cannot be a president candidate, right? But who knows? I'm still young, so I took that back. I don't want to exclude that possibility. Okay? Oh, I cannot. I'm not a U.S. citizen, so that stays valid. Okay? Stays valid. Okay? But you choose one of them as your final selection, but the remaining one automatically become what we call candidate keys. Okay? One last concept related with keys is that when you have, this is with respect to a single table, a single relational instance. What happens if you have multiple relational instances? Well, then there is something called candidate foreign keys, as illustrated from this figure here. So this is a student table, and this table is an enrolled table, which basically tells you which student has enrolled which class. You can imagine there will be another relational table out there which describe information related with the courses, which I'm not showing here on this slide. Right? But that table has a key called course ID, CID. And then this table basically captures the interaction between student and courses. A student chooses this course and so on and so forth. So that part we didn't cover in this class. We covered that in the undergraduate database class, which is how do you go from a user specification to a database design like this? Why it is student, course, and enroll? Why not student and course enroll in one table? Why not we do that? Why we do it in 3 tables? And those we don't cover here. We cover that in the undergraduate class. Okay? But taking this as the input, suppose somebody gave you a design like this already. You notice something, which is these green lines. Of course, these are imaginary lines. They do not exist in a database. But you can imagine there are these green lines between these 2 tables, which is to link record from one table to another. Why I say that? Because if somebody wants to come to this table, to the enroll table, and ask you, okay, give me the names of all students who have registered for topology 112. You look at this table, you are not able to answer that question because there's only student ID information. So what you have to do is take this and then go to the other table and find out the student record with that value and return the name. associated with that. Okay, and in the process of doing that, you actually follow this imaginary green line to trace record from one table to another. And this is something what we call foreign key. Foreign key. Why is foreign key? Because in order to do this trace, you must be able to uniquely identify a record from the other side, going one side to the other side. What that means is if I give you a student ID value here, it should be able to uniquely identify a single record from here, rather than say 2 or 3 or multiple records. Because if I do return you multiple records, which student name should you print? You will be confused. You see my argument? So it has to be unique in the other side, which means it has to be a key on the other side. And the fact that it is a key from the other table, but now sits in the current table, make it a foreigner. When I come to this, the recent discussion on NPR video on this, I always wonder why these people didn't call this alien key. Why? Because I'm an alien, right? When I first came to US, right? Because you are alien resident. So I always wonder why don't they call this alien key? Why they call foreign key, right? We can, why don't they? If they call this foreign key, why don't they call me foreign resident? Why they call me alien resident? Right? You have all these interesting things, right? So in my class, you can call this either foreign key or alien key. Okay. All right. So that's the concept of foreign keys. Okay. That's the concept of foreign keys. Okay. So with the concept of foreign key in place, we will introduce another thing called referential integrity constraint, which basically, if you do any programming in C or C++, you know there's something called pointers, right? There's a concept called pointer. There's a concept called pointer. And one of the major danger of programming in C or C++ is segmentation fault. Right? It's really hard to debug. Right? I don't want to go into detail why segmentation fault is so hard to debug, but it's related with the fact that, that you are using pointers to manipulate your objects. And root cause for segmentation fault is what we call doubling pointers. Doubling pointers. Doubling pointers are those pointers that was once allocated in your program that linked to an object, but later that object has been deallocated, but you forgot to quote unquote delete or deallocate the pointer. Then it becomes a dangling pointer, like a ghost pointer. Your program will wrongfully think that this pointer linked to an actual object instance, but that object instance actually, in fact, no longer exists. So when you try to follow the pointer and reference a value of that object, you will get an error, because instead of pointing to a useful memory space that holds value for the object, now that space becomes a bunch of junk bytes, which make no sense. When you try to make a value out of those, of course you get an error. Okay? So that's dangling pointer. That being said, if you understand that, integrity, referential integrity is exactly the same thing. You have foreign keys, right? What happens if this key points to a record, non-existent record from the second table?
Bad stuff.
Huh?
Bad stuff.
So that's kind of like a dangling pointer, essentially. Okay? So the referential integrity constraint basically says, okay, if you have a foreign key and a key relationship like we have just seen, you want to make sure there's no dangling keys, dangling foreign keys, dangling pointers. Okay? That's essentially what it says. And how do you specify primary key and a foreign key? Well, you specify primary key using the keyword primary key, and you specify the foreign key using the keyword foreign key, and also references. For example, in this example, the primary key of this table is student ID and course ID. Why? Because a student should be able to allow to take multiple courses, and a course should be able to allow a student to take a course to allow multiple students to enroll in it. So the combination of it is unique. Of course, if I tell you that's the university that you are in, then it's a really tough university. Right? Do you realize?
Never take the same course twice.
Yeah.
You can never take the same course twice.
Yes, exactly. If that's a key, if that's the primary key for this table, which implies you can never take the same course twice, which means you cannot fail. So that's why I say it's a really strict university, right? Or looking at the flip side, maybe that's a really good university. It never fails students, right? So everything has two aspects you can look at it, depending on. I always look at by the way, I always look at from the second angle. Right? It never fails students, so it's good. All right. So that's a primary key. And how you specify foreign key? Just say SID references the table from which it is a key. Okay? So it's very simple to do that. So integrity constraint, blah blah. You can look at this definition, but pretty much it is what I have just explained to you. Okay, the dangling point stuff. So and referential integrity. Oh, sorry. Oh, this is the integrity constraint. I should explain this. Okay. So we talk about referential integrity constraint, which is similar to dangling pointer in C or C++. To generalize that concept, we have something called integrity constraint, ICs. Don't read this as integrated circuit. All right? It's the same abbreviation, but it means totally different things. Integrity constraints are rules, if you would like to see that, are rules that your database must follow, or are constraints that your database must satisfy at all time. All time. Okay, I'll give you an example. For example, no student at this university should be younger than 18 years old, which means that each column in the student table must be having a value at least 18 or above. Okay, so that's an example of integrity constraint. And referential integrity constraint, as we just mentioned, is a special form of integrity constraint, because if it says that, okay, if you have a foreign key on this table, then it must point to a record that exists from the table where this is a key. You cannot point to a non-existent record. So it's a form of constraint that must be true at all times. Okay? So you may wonder where ICs come from. Well, integrity constraint for a database come from user specification. So whoever give you the user specification specify the constraint that he or she want to enforce against their database. Question?
From the warranty constraint, so basically if the reference table, the entry from a reference table is the user, then how do you deal with that?
That's a good question. So it goes to what happens under updates. Okay, it's actually related with the next concept I'm going to introduce, which is what is a legal instance. Right? A legal instance of a database is an instance where all ICs are satisfied. So you always start with the state of your database where it is a legal instance. You start from here. If there are no updates, you are only retrieving data and sending queries and get data back, then it will always be legal because you did nothing to the database. But once you have update, like he has mentioned, it may move from a legal state to an illegal state. Okay? You follow me? So what do you do in that case? Well, we're going to talk about that later on. When we talk about SQL, you have triggers and assertions in place to make sure that any action that causes a legal instance to become illegal will be rejected. So that's what database will do. Of course, there is a trade-off to enforce this legal state. Obviously, it's very expensive, as you can tell. Just think about our real life. If you want to make sure there's no crime, what do? Absolutely no crime. What do? You have to have one police at every possible location at any given time. Right? Even that is not enough. Why? Who says police must be trusted? So you have to have someone to monitor the police, who monitor somebody else. And this can go on, right? So enforcing constraint is really expensive. Enforcing constraint is really expensive. That's why in real database systems, oftentimes you only enforce constraints for really critical conditions. Really critical conditions. Like 50th bank must have this much dollar at all time. Okay? I'll give you an example. Just kidding, right? But you get the sense. You got it here, right? So the next slide is right to the answer of his question, right? What about how do we enforce referential integrity, integrity constraints? If you have any action that causing a referential integrity constraint to be violated, you reject it. Okay. In particular, for example, what should be done if a student tuple is deleted? Well, one thing you can do is, of course, you can reject it, but there are some other flexible ways of satisfying the constraints, right? One is you also delete all the enrolled records that reference to this student record, which means kind of like when you deallocate the object, you also deallocate all the pointers associated with it. Okay. Disallow deletion of the student tuple that's referred to. That's another way to say reject it. Okay. Or you can allow the deletion to happen and keep the enrolled record. You may wonder, when do you need this? Well, for example, when a student has graduated from the university, I no longer want to keep the student particulars, like name and address and things like that, but I do want to keep the student grade information for analysis and gathering statistical data for pass grade purposes. But I don't really care who is the student get this grade, but I do care there is a student at some point obtaining this grade from this class. Do you see the argument? In that case, you allow the deletion to happen and you do something about the foreign key so that it no longer reference to a non-existent student ID. Rather, you set the student ID for that enrolled record to some default value that you pre-agree on. So whenever you see this, you know this was once referring to a student, but later on has been deleted. So you never try to reference back to the student table when you see this. Okay. Similar argument can be made for the update to permanent key on student. Because why that's the case? Because update can be modeled. I'm not saying that's the way to implement it in real system, but they can be modeled as a deletion followed by insertion. That's simply what update.
So the last time we talked about nulls, can it be or should we have not have null?
The question, let me repeat the question, right? So there's a special value called null values, and then the question is, can a key or any key, primary key or candidate key, have null values? That's an excellent question. So it's system dependent. Some systems allow it. Most systems, as far as I know, will not allow a key to have null values. So typically, if you go with the last option, you set to some default values like 9999. Or 0000 or 111, some ID that nobody will ever take. Of course, you implement the system, you just keep this as a protocol, right? When you assign a student ID, don't take this special value off. Don't assign this special value. Relational query language, let's come back and revisit this SQL a little bit. So it's the most widely used, I think this is out of date, as I don't think the current standard is 99. I think the current standard is, I forgot which year it is, but every so often they will meet, the industry vendors they will meet and agree on a standard for SQL. So the reason for that is, this has a little bit of history behind it. At the beginning of the database age, which was in late 70s, early 80s, each vendor will come out their own database system and they will design their own query languages for their database system. And this quickly become a headache for users because in order to be a database expert, I need to learn this many different languages. That's just ridiculous, right? So these vendors, they finally realize it's in their best interest to unify the language. No matter which product you are selling, at least you train user once, then they can choose whoever is the database system, rather than try to tie them test with a particular query language. So that's why they meet and they form a standard for query language for relational database system. No matter whether you're Oracle, Microsoft, IBM, Google, if you want to design a database system, you follow the same standard for your query language. The specific implementation, of course, can be different because that's kind of like a black box. I just make sure the black box looks the same. The inside of the black box, how you do it, that's your own business. Okay? So that's where the SQL standard comes from. And a very simple example of SQL statement is this. You select a heuristic from schema where followed by a condition. In this case, what all I'm doing is find all students whose age 18 years old, whose age is 18 years old. Okay? So that's what you do. And you may also replace the heuristic with a list of attributes. A list of attributes. If you supply a heuristic sign over there, that means for all the qualifying records, print all its attributes. If you replace that with the attribute list, this basically means for all qualifying records, print only the values for those attributes. Okay? This is a query over a single table. What about query over multiple relations? Well, you use the from clause to specify multiple relations, and you use the where clause to specify the conditions to kind of quote-unquote glue these relations together. So in this case, I'm looking at student name and course ID from student and enrolled, where student get an A in that class. Do you follow me? Okay. So given this instance of enrolled and the preceding student instance, I don't have to go back and check, but you can check this if you want to. You get this results back. You get this results back. Okay. So how do you understand this SQL statement? Well, the semantics of a query is very simple. The conceptual evaluation method. I emphasize the word conceptual evaluation. Why? Because this is just a way to understand what it does. It doesn't mean the system actually will execute the query using this particular approach. Okay, because why? Because using this particular approach to execute a query will be super expensive. But it's a very easy way to understand what it does. So what it does and how it does are two different things. What it does and how it does are two different things. The SQL is really a way to specify what to do, if you think about it, right? And the whole idea behind a relational database system is how to do it efficiently. And the conceptual evaluation for SQL statement is you do the from clause, you compute the cross product from student and enroll, and then you do the where clause. You check condition, discard tuples that failed the condition, and then you delete unwanted fields. So to give you an example, this is the cross product between student and enroll. What is the cross product, by the way? Cross product between two tables is a concatenation of every possible pair of records from the two tables. So first record from the first table pair with all the record from the second table. Second record from the first table pair with all the record from the second table. You go on and on. So if you have n record from the first one, m record from the second one, you have n times m number of records in the cross product. Okay, you form the cross product, check the condition, keep the rows in the cross product that satisfy your condition, and then finally remove unnecessary attributes. Okay? That's why only this row satisfies the where condition, IDs are the same, and weight is A, and then you product out the final attribute you want, which is name and course ID. Alright, that's a summary we can skip. Let's move on to the next slide. Once we understand the relational model, we also want, of course, we want to have an in-depth understanding of SQL, which we will do that quickly in Thursday's lecture. But before we do that, we need to understand the theoretical foundation behind the design of the SQL, structured query language, right? So there is something called relational algebra. It's a relational query language that is used to express SQL, because inside a database kernel, it doesn't understand SQL. It understands some simple symbols. These symbols are what we call relational algebra, which we will discuss next. So you can skip this. That's pretty much what I said just now. And there are 5 basic operators in relational algebra: selection, production, cross product, set difference, and union. That's all. So it's a very simple language, but surprisingly, its expression power is super rich. So it can express a lot of different query syntax. So let's look at each one of them in turn. Let's look at the selection operator first. And for that, I will give you a number of instances to use as running examples. In particular, we're going to use this boats and sailors example, right? These are boats, these are sailors, these are reserve table, who reserve which boat. And for the sailors, for the argument's sake, I will provide 2 different instances of the same schema, just to illustrate the different results you may get when the instance is different. Okay? The first one is projection. Projection is simple, right? It's written as a Greek letter pi, followed by a list of attributes as a subscript, followed by an input relation. Input relation to the projection operator. Okay, so this is a bracket. So it could be a single attribute or it could be a list of attributes. All it does is to take a column out from an instance or a set of columns out from an instance. That's it. That's all it does. The only tricky thing you need to pay attention to is relational algebra is closed. So what does it mean by is closed? Well, I'll give you another example that you can make a connection to. If you think about integer, the set of integers as your object, and you define a number of operations on this set of integers. What are some typical operations you do? Well, plus, division, multiplication, and minus, right? So with respect to the set of integers, I argue this is closed. Why? Because you take 2 integers as input, you produce something that is still in the same field. That's still an integer. This is, but this is not. Division is not. You take 2 integers as input, the output is not something you can describe using the same model. You no longer comply with your model. Then it's not closed. Do you follow me? For integer, the set of integers. So that being said, relational algebra is closed, which means you take the input that conform to the relational model, and the output is guaranteed to be in the same model. The output must be a relational instance as well. That said, that's the particular thing about projection that you need to understand. Projection, because of this requirement, which says the output must be a relational instance as well. And because it is a relational instance, we recall the discussion we just had. For a relational instance, no 2 records can have same values on all fields. So once you do a projection, you have to potentially worry about removing duplicates. So give you an example. This is my input. If I do the projection on name and rating, what do I get? I get that. And this is fine because there are no duplicates. But if I print out the age, instead of getting 4 values, I will only have 2 values in the output. Why? Because if you look at the 4 values you get, now each record is a single attribute in the projected output. And that no longer satisfies relational instance requirements because now you have duplicated records, but you cannot have a duplicate record in a relational instance. So we have to remove duplicates. Okay? A question I pose to you guys to think about, I will ask that in the beginning of the next lecture, is how do you remove duplicates efficiently? Okay? How do you remove duplicates efficiently from a set? Because I can view this as, of course, that's a EU form question, right? When I say a set, by definition, a set is duplicate free. So how can you remove you can, of course, I can ask you to remove duplicate from set. Then you should feel really happy about it. You should say, oh, that's a really hard question. Let me go and do it. You spend 2 days doing nothing, come back. Oh, I figure You don't have to do anything. So let me reform my question. How do you remove duplicates from a multi-set? A multi-set is a set, is a special set where you may have duplicate elements. Okay. So that's projection. What about selection? Selection is a Greek letter sigma. Basically, select a subset from the input relations. That's all. What are those what are those records that go into the subset as the output? Well, all the records from the input that satisfy your selection condition will be in your output. So, for example, this will give you these two. Now, because relational algebra is closed, you can compose relational algebra operators any way you like, because they expect something that's relational as input, and they produce something that's relational as output. You can view this as a streaming process, like pipeline. You can combine them any way you like. So you can feed the output of a selection to the input of a projection and get the final results you want. Okay, one question I ask here is, do you need to worry about duplicate elimination for selection? How?
No.
Why? Why not?
Because when we get the results, the numbers, after that we will somehow projective to see, right? So projections will be after that.
Projection will be, yeah, projection, but why selection doesn't have to worry about duplicate elimination?
Because you already have a set. All the columns are all the rows are distinct.
Okay.
And if you're removing more rows, the rest of them still can't.
Because the input to a selection is a relational instance, which is a set, which means it's duplicate free. If I give you something duplicate free and you choose a subset from that, it's guaranteed to be duplicate free. Union and set difference, these are super easy, right? You just union and you just find the difference. Okay? The only thing goes here is that the two relational instances that you supply to a union and difference operator must be quote-unquote union compatible. You cannot union a set of integers with a set of strings, for example. They must be union compatible. What do we mean by union compatible? Well, they must have the same schema. They must have the same schema. And for union, if I first of all, you satisfy this rule of cumulative rule, right? You can swap the order and stay the same. For intersection, for set difference, though, that's different, right? Right? And for which one of this, you need to worry about duplicate elimination, right? Well, this is an easy question to answer once you draw a graph to see what's going on. Union is what? Union is this plus this plus this. So you do need to worry about duplicate elimination because potentially there are duplicates here. What about set difference? Well, R minus S is this. S minus R is this. It's a subset of a set that's duplicate free, so it doesn't have to worry about duplicate elimination. Of course, there's a special case of all, which is they do not intersect at all. Then in that case, you don't have to worry about duplicate elimination for union or this. That would just be R or S itself. Okay. What about intersection? Remember, the last operator in relational algebra is cross product, which I will skip because I already explained to you what a cross product means. So why there's no projection? Can someone tell me why there's no projection? Oh, but not projection. Why there's no intersection?
So you can express it in terms of union and set.
Because so there's no need to have this operator. And because of this, inspired by this observation, there are a number of other operators. We do not introduce them in relational algebra as the basic operator, but they will be expressed by the combination of the basic operators. And of course, those are not as easy as this, but we will talk about that in Thursday's lecture. All right, with that, we stop right here. All right, thank you.